Alright, camera's still working. Very good. So, continuing on, having introduced the shape operator, we make a couple of important definitions. The Gaussian curvature is the determinant of the shape operator at a point, and the mean curvature is 1/2 the trace of the shape operator at a point. And of course we can think about these as functions on the surface if we allow p to vary. So they give us a real valued function, the formula of which is a little bit complicated, but the purpose of this current talk is to sort of describe some computational techniques to get at how to calculate these things. And so of course if you know the eigenvalues of the shape operator, well then they're k1 and k2. These are the so-called principal curvatures, and of course the determinant's the product of the eigenvalues, and the trace is the sum. And since it's a 2 by 2 matrix, there are just two eigenvalues. Since it's a symmetric and real matrix with respect to any basis, we know that there's just two eigenvalues, and these are standard results from linear algebra, that the determinant is the product of the eigenvalues and the trace is the sum of the eigenvalues. So wonderful. And so if you think about the Gaussian curvature, well, there are three cases: positive, negative, zero. If it's positive, that means that either both eigenvalues are positive or both eigenvalues are negative, right? Both principal curvatures are positive, both principal curvatures are negative. Either the surface is bending up towards the normal or it's bending away from it. That's when they're both negative, that's when they're both positive, I believe. And if one is positive and one is negative, then the product is negative, and so you get like a saddle. We're bending towards the normal, bending away from the normal. And then of course if the curvature is zero, then we have what's called a planar point. Alright, and I think that would be an example of an umbilic point. Let's see here. So, a really good example, and I wish I could find my torus, but I have a styrofoam torus. It's great for this, but it's maybe it's in my office or something at the moment. But in any event, if you can imagine this, I mean, I have something, but maybe too big to see. I'm not sure. I'll try. See, it's probably, first of all, this doesn't quite do it justice, because the torus is got smooth. It's not like this dryer hose, which is all bendy. But inside, if the normal's outward pointing, you've got the surface bending up towards the normal on the inside, but it's bending away as you go along these lines, right? On the other hand, if you're out here and the normal's pointing outward, then the surface is bending away from the normal this way and that way. So as you can see, it's positive curvature on the outside and it's negative curvature on the inside. And that's what, you gotta find a smaller hose. I was tempted to take my Benjamin's pool noodle and cut it for this purpose, but I fear Benjamin. So on the torus, you have two regions. You have the region with negative Gaussian curvature on the inside, and you've got a region with positive Gaussian curvature on the outside. And if you can envision it, sort of there's this top line, and there's also a line on the bottom I didn't try to draw, where you're shifting from negative to positive, and on that line, a curve really, of course. On that curve you have zero Gaussian curvature, and of course those aren't planar points, right? One of the principal curvatures actually is zero, but the other one is not, right? So, yeah. I'm trying to think here. There. Yeah. Okay, so So next up, formulas. All right, so what are some formulas for the Gaussian curvature? So if we have V and W linearly independent vector fields, or well, this can be vectors at a point, TPM. Of course, you could let the P vary, and then you could think about these being pointwise linearly independent. They give you a pair of linearly independent vector fields, if you like. Although I really want pointwise linear independence. Anyway, you can prove these formulas. The cross product of shape operator on V with shape operator on W is the Gaussian curvature times the cross product of VW. And likewise, the shape operator on V cross W plus the V cross the shape operator on W is actually twice the mean curvature times V cross W. And the proof of star and star star is actually pretty elementary. All you have to do is, well, because this is linearly independent, means it forms a basis, which means that you can write S of V, whatever it is a linear combination of the basis, namely V and W. And likewise for W, we can write C and D as the weights for the value of S of W. And with that in mind, that makes the matrix of S with respect to this basis. Again, if you want me to, I could clutter things up and say, okay, well, this is basis beta, right? And this is the matrix with respect to beta in my notation. But anyway, just trying to connect back to that lecture again. I mean, you can always add more notation to be more detailed in almost all of this stuff. The principal offense throughout all of these things is like there's a point dependence, which is capriciously omitted or not omitted. The point dependence is especially, I don't know what the word is, capricious, I guess. Anyway, so there's the matrix, and that makes the determinant AD minus BC, and that makes the trace A plus D. Notice that when we take the cross product of S of V and S of W, we get this cross that. Of course, V cross V is 0, W cross W is 0. That just leaves us with AD, V cross W plus BC, W cross V. But to anti-commute them, I get a minus here, but that's the determinant, so there's star. And star star is almost the same calculation, so it's like, okay, that plus that is, well, it's even easier, because when we take S of V, which is AV plus BW cross W, the W term drops out and you're just left with A. This one just drops out and just leaves you the D term, V cross W, and so you get A plus D, which of course is twice the mean curvature, and there's the star star formula. Now, so let's see here. Now I think this calculation down here is forward-looking. Right. I mean, this is Lagrange's identity, the dot product of two cross products. It's this determinant of this matrix of dot products. So when you take the dot product of the shape operator V cross the shape operator W with V cross W, you get this determinant here, right? But on the flip side of things, you also get, so this is from Lagrange's identity. However, can you see this? I think I'm in frame or not. I think I'm in frame. Gotta stand up. I'm right on the edge of things. All right, so this equals to that is Lagrange's identity, which is right here. The fact that this is also equal to that comes from star. So take the dot product of star with V cross W. You get this on the one side, and you get K V cross W dot V cross W on the other side, which of course is the length squared. So, cool. What does that mean? That means, come on, that, well, I think I've shown some of you this already this semester, but here it is. Here's a proof of Lagrange's identity using the double delta identity for the product of the contracted epsilons, contracted Levi-Civita symbols. Anyway, there's the proof of the Lagrange identity. but not really, I mean, not wrong, but in any event, let me connect the dots here. So, you know, this was, we have this is k times length of v cross w squared. So if we solve for k, we get this formula because the denominator here is, you know, this is literally the magnitude of v cross w squared, but the formula is written this way to make it look symmetric. I don't know, what is it good, is it bad, I don't know. And the same denominator down here, this is the magnitude of v cross w squared. And again, the derivation is very similar. See, because we have this identity, this plus that is 2h v cross w, so when you take the dot product of this expression here with v cross w, we use Lagrange's identity on each piece to get one determinant with respect to that, another determinant with respect to that. And that is exactly what's over here. I think I might have a little bit more, let's see here, let's see if I have the details. I mean, I'm not sure if I have anything that's, I mean, I have this, which is, you know, essentially the point is you have this is equal to that. So you take the dot product of both sides with v cross w. And when you do that, the Lagrange's identity gives us this and gives us that. And that's the identity we're just looking at. So, yeah. Now, another thing we should know is that you can, so if you have, of course, if you have the principal curvatures, it's easy to calculate Gaussian curvature and mean curvature because Gaussian curvature is the product of the principal curvatures and the mean curvature is the average of the principal curvatures. It's k1 plus k2 over 2. Which of course is why it's called mean curvature, right? But on the flip side of things, you can also calculate the principal curvatures from a given mean and Gaussian curvature according to these formula right here. And the proof of that is relatively straightforward. So it's just straight algebra. The mean squared is k1 plus k2 over 2 squared, which gives us the k1 plus k2 over 4. That squared upstairs, so you square it out. You got yourself a k1 squared over 4, you got yourself a k2 squared over 4. You have 2 k1 k2 divided by 4, which is k1 k2 over 2. But then you subtract the Gaussian curvature, which leaves you with a net plus, excuse me, a net minus 1/2 k1 k2. And factor the 4 out, that leaves us with, come on man, k1 squared minus 2 k1 k2 plus k2 squared, which is of course k1 minus k2 squared over 2, right? And then, let's see here, then what? The claim is that you can get, so okay, so that gives us that, I'm going to go back to my other page. Let me flip the page here. Let's see if that does it. No, that's it for here. I mean, this is not wrong. I think need a little bit more to see why that formula is true. So, so this is where we got to h squared minus k is 1/4 k1 minus k2 squared. So we take the square root, and that gives us plus or minus the square root of h squared minus k is 1/2 of k1 minus k2, right? But h is equal to k1 plus k2, right? So if I add h to this, that gives me, what happens? The k1 plus k1 over 2 gives us k1. The k2's cancel, and you're just left with k1 is h plus the square root, right? On the other hand, if we take the difference of, let's see here. Well, if we can solve for add one way we get K1. If we subtract the other way we get K2. So I'm trying to find the words. It's really just algebra. So if I take H minus this, then the K1s cancel and the K2 adds to give me K2. So there you go. These are the formulas for principal curvature 1 and principal curvature 2 in terms of the mean and the Gaussian curvatures. All right. And also, next up in this story, first told by O'Neill, I guess that's not true. I mean, many people told the story before he did, but I think he told the story very well. Anyway, so surface is flat if it has Gaussian curvature 0. Surface is said to be minimal if it has mean curvature 0. So flat surfaces include planes and cylinders. And a minimal surface is an example of that would be a helicoid, which we'll talk more about here later in this lecture. Of course, a minimal surface also has Gaussian curvature negative, because the only way you can get the mean of the principal curvatures to be 0 is if they have differing signs. And if they have differing signs, that implies that the product of the principal curvatures must be negative. All right, so minimal implies negative Gaussian curvature. That, on the face of it, that looks like a scary test question, but actually I could think of, I mean, that's a really actually pretty friendly test question, isn't it? All right, if you know what you're doing. So moving on here. All right, so as I just said, flat, Gaussian curvature 0, minimal, mean curvature 0. And here's some pictures. The plane, of course, has 0 curvature. A cylinder, which you could, of course, form by, you know, doing one of these deals here. Also, you know, curvature 0. All you have to do to have curvature 0 is to, well, there's a lot of ways to have curvature 0, but you just need to have a line, I suppose. So you have to be careful, because ruled surfaces don't necessarily have curvature 0, and yet they've got lines in them, you know. Got to be careful how you say that, but definitely cylinder has curvature 0. And it's because one of the principal curvatures is 0 at every point in the cylinder. And then, of course, a sphere has principal curvatures -1/r at each point. So the Gaussian curvature is 1/r². Mean curvature is -1/r. And then this here saddle surface at the origin has mean curvature 1 and Gaussian curvature -1 and mean curvature 0. We'll see the general formula for this before too long. Let's get on to it. So that concludes section, excuse me, 5.3, I believe. If I can find my... Did I get things out of order here? Huh. Oh, okay, I know what happened. I see, the reason I've confused myself is I have just left the end of my quote-unquote lecture 15 here, and I was putting it together with my lecture, what was it? 16, yes, which we're about to start. All right, and I would remind you that these are scanned and posted as PDFs on my Differential Geometry website. Hopefully I'm improving on them a little bit here. I have spent several hours working back through the book, and I was all ready to give a lecture in class, and then there was an indication of a storm that was given to me. Although I must say that the weather was very calm this Wednesday at night. Very calm. Annoyingly calm, I would say. Anyway, lecture 16. So here we are. Calculational techniques. All right, this is section 5.4 in O'Neill. All right, so just really a lot of formulas in this section, but I tell you what, they're really worth it. And well, I like formulas. I think a lot of math majors get into math because they like formulas, and then the formulas go away at some point more often than not. But anyway, so we define warping functions E, F, and G. I think this nomenclature goes back to like Gauss. So there's E, F, G, L, M, N. There's just a whole alphabet soup of stuff in here. But given a patch, you can calculate the warping functions. E is x partial u velocity dot partial u velocity. So it's the length of the partial velocity with respect to u squared. Likewise, g is the length of the partial velocity with respect to v squared. And f is xu dot xv, which is the length of e times the length of, well, it's the length of, excuse me, it's the square root of e times the square root of g, because it's the length of xu times the length of xv times cosine theta, right? So these, again, are called the warping functions. In the event that your patch has f equals to 0, that's called a orthogonal patch, and those are pretty nice. Now, if we take the dot product of two vectors that are expanded in the xu xv basis, the formulas for the coefficients are a little bit complicated because, well, you have E, F, and G appearing in the formula, right? And if f is not 0, there's this middle term, which makes it look, I mean, usual dot product, we just have v1w1 plus v2w2, right? But when E and G are not necessarily 1 and f is not necessarily 0, the dot product of v and w with respect to this basis, it involves these E, F, and G. All right. The other thing is we're often interested in the normal vector field, right? The normal vector field is xu cross xv, and if we want a unit normal, we have to divide by the length of xu cross xv. But the length of xu cross xv is, in fact, the square root of eg minus f squared by Lagrange's identity, right? So the length of the cross product squared is the dot product of this with that, I mean this with itself, times this with itself, minus the dot product of this with that squared, right? And so that gives us eg minus f squared. So the length of the cross product of xu with xv is, in fact, the square root of eg minus f squared. And a little bit later in section 5.4, he gives this thing a name because he gets tired of writing it. The letter that has been declared for the square root of eg minus f squared is w. So you could write that the unit normal is xu cross xv divided by w, where w is, I'll even write it up here, w, because it's almost, I mean, it's, I guess it doesn't have the same status. Do we make these kinds of value judgments in mathematics? I don't know. Anyway, so it's nevertheless, it said it's 15 minutes of fame, but it's probably something more like 160 years of fame. So there you go. And then I'll remind you that we have notation for, if I use like big X for the patch, so if it has component functions x, y, z, then like xuu means we partial differentiate the x, the y, and the z component separately. And I don't usually write the square out there. I write it in here. Come on, man. What's wrong? Look at just all of a sudden I just put these two 2's out there. What come on. What's that? Tell you what. It's very offensive. I'll fix it. There we go. All right. I should have made that brown. Not a very good cover up. I highlighted my mistake. Okay, so there we go. Second partial velocities with respect to u and v and uv. Just these are specifically what we mean by those formulas, of course. Just like calculus 3, in fact, right? And so, of course, we need more letters. So LMN is going to be, L is going to be the shape operator on xu dot xu. M will be the shape operator on xu dot xv. And N will be the shape operator on xv dot xv. we proved before that you could either write this or you could write that, and we used that to prove that S was symmetric. In fact, let me remind you that, in fact, these we had formulas before. I think I'm actually about to get to it on the next page here, but just in case I don't, well, maybe I should just leave this alone. Let me go on here. But I'm going to do it. I'm just going to bring this in here for a second. But we had previously proved that, you know, this dot that is xuu dot u. This dot that is xvv dot u. All right, for what it's worth. And in the middle, it's actually, this works out to xuv dot u is x of uv dot xv. So you can calculate Lm and n if you know the unit normal and you've calculated the acceleration and the, let's say, mixed acceleration of the patch with respect to the parameters. Right. And more than that, we can use Lm and n to write formulas for the Gaussian curvature and the mean curvature. And here's how they work out. The Gaussian curvature actually is ln minus m squared over eg minus f squared. And the mean curvature is glen minus 2fm divided by 2 egg f squared. This is really 2w squared, and that's w squared, right? And my proof here, I'm sorry, I've been watching some Merry Melodies recently. I think I got a little bit of that little varmint chasing guy with the mustache. What's his name? Anyway, so you just put v equal to that and w equal to that in the formulas at the end of lecture 15, and when you do that, it pops out of that those two formulas that we found. Let me actually show you this specific calculation here that I'm indicating, which is this. So we had before that k was, you know, that divided by that. So when we put v equal to xu and we put w equal to xv, this gives me L, this gives me n, and we've got m and m here and here. So that's ln minus m squared. And downstairs, it's the magnitude of v cross w, but that's w squared when v is equal to xu and w is equal to xv. So that's why k is equal to that. Very, very simple. And h, on the other hand, is, this was given by this formula, but we had v's and w's before, but now we're putting v equal to xu and w equal to xv, and when we do that, that gives us L, G, and this is F, and that is M. Sorry, my scratchy writing here is not quite, that's E, that's F, that's M, that's N. So that gives us LG minus MF, and then EN minus MF, but the two of them's, so it gives you LG minus EN minus 2MF, which of course is the same as glen minus 2MF over 2W squared. So there you go. There's your pretty nice formulas, believe it or not. Because all of these different ingredients are pretty straightforward to calculate, so then you just put them together and you got it all. As opposed to, well, I don't know, or you could pick a basis, calculate the shape operator, and do the linear algebra. I mean, it's not so much harder, really. But here they are. I mentioned these before. Mention them again. Lm and n we can get from u.xuu, u.xuv, u.xvv, and right. So finally, all right. So now that we've been in the midst of formulas, linear algebra, and the rest for quite a while, and now we actually have an example, the helicoid. So we try to just unwrap a little bit of it one bit at a time. All right. So first of all, the let's see if I can move it up a little bit here. All right, so first of all, this is the parameterization of the helicoid. All right, u cosine v, u sine v, bv. All right, and that's parameterization of the helicoid. And I want to say was a ruled surface that we created using like the unit Frey-normal. There's lots of pictures of it in O'Neill. I won't attempt one here. And so once you have that, you can calculate the partial velocity with respect to u, with respect to v. When you take x u, there's no u, so you get 0. Acceleration, the mixed acceleration, uv, you get minus sine, cosine, right? Notice it doesn't matter if you differentiate that with respect to v. If you differentiate this with respect to u, all paths lead to the same formula for xuv. That's because xuv should be, of course, equal to xvu, right? It gives you a little check on your calculations, though, for what it's worth. And, of course, xvv, well, that's this guy. Very straightforward calculation, right? Now, e, remember what's e? E is xu dot xu. So xu dot x, here, I'll write you over here. Now let me just kind of, I'll probably regret that, but oh well. I think this is probably going to go in the trash after this anyway, so. Here, we have e is xu dot xu, right? So xu is this, xu dot xu is 1. F is xu dot xv. Xu dot xv, we get cosine sine minus sine cosine plus 0, so the sines and the cosines, pluses and minuses cancel. We get f equal to 0. And g is xv dot xv, which gives us u squared sine squared plus u squared cosine squared plus b squared. Sine squared plus cosine squared factors out with u squared. That gives us u squared plus b squared. It's the length squared of xv. And so there it is. G is, so there you go. G is u squared plus b squared. This is in fact an example of a orthogonal patch because f is equal to 0, which means that the calculation is nicer than it would otherwise be. And so we go on. And we calculate the normal vector field by taking the cross product of the partial velocities. All right, we get this. As a check, this should be perpendicular. If I did the cross product right, it should be that this dot with that and this dot with that, dot with xu and dot with xv should both be 0. 0. And I get minus ub sine squared minus ub cosine squared, so I get a net minus ub, and then I get a plus bu, so minus ub plus bu, 0. So indeed, this is perpendicular to both of those, so I would have to be fantastically unlucky to have gotten that calculation wrong. But there it is, the normal vector field. And then we have to divide by w, right, which is what? Eg minus f squared, and Eg minus f squared is just g in this case. All right, and well, square root of that. Remember, the square root of Eg minus f squared is what w is. And okay, so anyway, there you go. This is a unit vector, unit normal, right? And now remember L, M, and N. How are L, M, and N defined? L, M, and M were defined by, you take the acceleration dot u, right? Actually, they're right. Sorry. Let's keep my stuff in order here. Put it back. I'll just leave this whole page open for your perusal. So here's the L, M, and N up here. So I take u dot xuu, u dot xu, well, xuu dot 0. So that makes L equal to 0. M is u dot xuv. XUV is this guy. And that gives me minus b sine squared minus b cosine squared. So it looks like it's going to give us a minus b. Wait a minute here. Hey, where'd my minus b go? Oh, it's still in process. So there's the minus b, So I get minus b over the square root of u squared plus b squared. That's my m. And n is equal to 0 because xvv is perpendicular to the unit normal in this case. Yeah, this dot with that is 0. So L is equal to 0, N is equal to 0, M is equal to that. Moving along here. So we have calculated so far L is equal to 0, M is equal to minus b over the square root of b squared plus u squared, N is equal to 0, E is 1, F is 0, G is b squared plus u squared. So put it all together into our handy-dandy formulas for Gaussian curvature and ln minus m squared over eg minus f squared, and that works out to, lo and behold, minus b squared over b squared plus u squared squared. So there you go, that's the Gaussian curvature of a helicoid. Interesting, you know, the helicoid is parameterized by both u and v, right? And the Gaussian curvature depends only on u. So it doesn't matter what v is, the Gaussian curvature is determined totally by whatever the value of u happens to be at the point in question. So that's kind of interesting. And the mean curvature, on the other hand, is, well, there's enough things that are 0 that it works out to 0. And so that means the helicoid is a minimal surface, as I mentioned before, and the Gaussian curvature is in fact negative. See that because this is negative. I'm just observing that formula is negative, right? And what are the principal curvatures? Well, we can use the other formula we found for principal curvature a second ago, right? Now that we know the Gaussian curvature and the Gaussian curvature and the mean curvature, I know that h plus or minus the square root of h squared minus k gives me k1 and k2. So since h is 0, this just simplifies to the square root of minus k plus or minus square root of minus k. The minus cancels the minus, and we get square root of b squared over, so it's the square root of square, which just gives us plus or minus b over b squared plus u squared. So there you go. Those are the principal curvatures. As you expect, one's positive and one's negative. We anticipated that because, of course, the Gaussian curvature was negative. Well, also because it's a minimal surface, and as we commented, minimal surfaces have to have negative Gaussian curvature. A lot of different ways to look at it. And of course, it might even be interesting to to try to actually calculate the shape operator directly, right? But how would you do that? How would you calculate the shape operator directly here? That's the thing, is we don't have to, because we have all of these lovely formulas that don't involve sorting through the nuances of the covariant derivative, which we could do, right? But this is very nice. So, and we have another example. You may recognize this. This is a cylinder. All right. So I think this example, I don't think this one is in the book. I'm pretty sure that I know I got the helicoid from O'Neill, and I believe the saddle surface example is also in O'Neill, but I don't think he had the cylinder. I think I just added that here. Not that it was, hard or anything, but just a second, I'm looking. Yeah, O'Neill has the saddle surface and the helicoid. Yeah, page 227. So, for the record, that's not a copy. That's just how this book generally comes unbound after a while. I wish somebody would reprint this thing and do it justice. But anyway, okay, so here's the parameterization of the right circular cylinder of radius r. All right. So you calculate your partial velocities, and you calculate your e, your warping functions, your e, your f, your g. pretty simple. Again, this is a orthogonal patch because f is 0. The partial velocities are easy enough to calculate. Two of them are 0. Only x, u, u is non-zero. And that gives us that L is minus r, m is 0, and n is 0. I say this, but actually this can only be understood once you've calculated the unit normal, which I do down here. So the unit normal is cosine sine 0. And so that's r hat in the usual Calc 3 lingo. And so that the dot product of u with xuu is minus r. Otherwise, the dot product, of course, with 0 is 0. And so, yeah. So there's your EFG LMN. And so we can calculate the Gaussian curvature is 0 minus 0 squared over, I guess it's r squared, right? 0 over r squared, which is 0. So the Gaussian curvature of a cylinder is 0. And the mean curvature it works out to minus 1 over 2r. So that's pretty neat. Notice that I claimed that the cylinder was flat before. Now I have proved it for you. This is the calculation. This is the analytical proof that the cylinder, the right circular cylinder, is in fact flat, that it has 0 Gaussian curvature. All right. The saddle surface, I gave you some kind of, sketchy geometric calculation of the curvature, the Gaussian curvature at the origin for the saddle surface. I mean, there was a lot of holes in that argument. This is much better. So here it is. The Monge patch, we use x and y as parameters essentially. X equal to u, y equal to v, so we got uv and then uv for z. And so here's your partial velocities, your unit normal you get from xu cross xv. And so you can check that this vector dot that is 0, this vector dot that is 0, and the length of this is exactly the square root of v squared plus u squared plus 1, which is that. So there's your u, here's your accelerations, xuu, xuv, where's my xvv? Dude, where's my xvv? Oh, duh. So obviously, I'm sorry, I can't read my own writing. xuu and xvv are both 0 because xu and xv are both linear here, in u and v. But why would they be 0? Oh, because xuu, it's got a v dependence, this one's got a u dependence. I see it, never mind. Duh. Okay, so they're both 0, which makes both L and N be 0, only the M, as in mummy, the mixed partial, 0, 0, 1 dot this gives me, well, 1 over the square root of 1 squared, 1 plus u squared plus v squared. There it is. So here's your EFG So we can calculate the w squared eg minus f squared, which in fact here is 1 plus u squared plus v squared. And that's the denominator in the formula for the Gaussian curvature, ln minus m squared over eg minus f squared. And so there you go, minus 1 over 1 plus u squared plus v squared squared, right? And the mean curvature, Glenn minus 2fm over 2 times eg minus f squared. Eg minus f squared with 1 plus u squared plus v squared. And let's see here, a lot of this stuff is 0. The L is 0, the N is 0, so it's just the minus 2fm. F was uv, and m was this stuff here, so that's why we've got 2uv over the square root. So we get a total of 1 plus u squared plus v squared to the 3 halves downstairs, and a minus uv upstairs. And forgive me if I take a second to do this. I just feel like I've accomplished something. Yeah. All right, there we go. And so, of course, if you go back to using x for u and y for v, it's a little bit more insightful, I think. This is the formula for the Gaussian curvature at an arbitrary point on the saddle surface. This is the formula for the mean curvature at an arbitrary point on the saddle surface. And you can see what happens when we put x and y both equal to 0. That gives us z equal to 0. So at x and y both 0 at the origin, we have mean curvature 0, right? And we have Gaussian curvature -1. And I will just remind you that, previously I gave you some kind of like kind of sneaky sideways arguments just to argue that the matrix of the shape operator was in fact 0, 1, 1, 0 at the origin of the saddle surface. So in that case, the trace is 0, so half the trace is 0, and the determinant was -1, which gives us, that reproduces. Our new formula reproduces what we found before, right? But here you go. This is analytical proof of the Gaussian curvature and the mean curvature of a saddle surface at an arbitrary point. So that's kind of nice. And while I was at it, I decided to do a couple of your homework problems. They haven't been assigned yet, but they probably will be. So number 8 concerns an orthogonal patch. It says if f xu dot xv is 0, show that the formula for the shape operator is just L over E times xu plus M over G times xv, and similarly for S of xv, right? And so this relies on a little bit of linear algebra that I'll just write out here. So here's a theorem. If we have basis beta, which is say v1, v2, vn, where vi dot vj is equal to 0 for I not equal to j, and let's say vi is not equal to 0 for all I. In other words, we have a set of orthogonal non-zero vectors, then and let's suppose the beta is a subset of Rn, right? Then beta is basis, and if, I know I capitalized that, if x, let's say, is equal to the sum over I equals 1 to n of ci vi, we have that the formula for ci is equal to x dot vi divided by vi dot vi. All right. So let me prove that for you. Take us but a second here. Proof. So suppose beta is as above, and let x equal to, the sum I equals 1 to n ci vi, all right. Then if we take x dot, I'll use j, vj, that's equal to the sum I equals 1 to n of ci vi dotted with vj, right? But then by properties of the dot product, I can bring the sum out, and I can bring the constants out, and I've just got vi dot vj, right? So I get a sum of dot products. But what's the deal with this? Well, it's 0 for I not equal to j, right? So this just gives us c j vj dot vj. That's the only term that survives. So therefore, cj is, what is it? It is x dot vj divided by vj dot vj. Now that is precisely my claim in the theorem, right? So oftentimes we work with orthonormal bases, which are even nicer, right? An orthonormal basis as opposed to an orthogonal basis. An orthonormal basis is a orthogonal with each vector having length 1, right? Orthonormal adds the condition that the length of vi is equal to 1 for all I. All right, and so that's an even nicer thing. In that case, get that vi dot vi is equal to 1. So in that particular case, that more special case, orthonormal case, the coefficients are just given by dot products of the vector with the orthonormal basis. So I'm relying on this background information when I solve number 8, okay? In the case that we just have two vectors that are orthogonal, as in the cases here, I say orthogonality of the basis xu and xv of TPM is very nice. And so S of xu is a vector in TPM, so that means I can write it as a linear combination of xu and xv, which are a basis. And to get the coefficients, I take S of xu dot xu divided by xu dot xu, and I take S of xu dot xv divided by xv dot xv. That is using what I just wrote out. In the case n equals to 2, and like this is my v1, and this is my v2, and in red, and, you know, this is like xu, that's like xv, and that's it. N equals to 2, so that's, you know. Now, furthermore, by definition, that is L. By definition, that is M. And downstairs, that's the warping function E. That's the warping function G. And similarly, when we do xv, so this gives us the M, and that's the warping function E. This gives us the Lm N, and G down there, the warping function. So there you go. In other words, this is actually another way you could look at this problem, is it gives us that the matrix of S in the xu, in the patch basis, the orthogonal patch basis, that the matrix of S in the orthogonal patch basis is given by like L over E, M over G. That's the coordinate vector of xu. And then the second one is M over E and N over G. Right? And you could recover the formulas for the Gaussian curvature and the mean curvature in this particular case by just taking the determinant of this matrix or trace of it divided by 2. All right, so that's kind of neat. But I don't know, it's not needed either because we have these really nice slick formulas for you know, Gaussian curvature, mean curvature anyway, but whatever. Now here's more. The patch is said to be principal if f is equal to m is equal to 0. And we can show that xu and xv principal for a principal patch. Ooh, I think I have a suspicion. Oh. What does that mean? They're what? These are principal directions, right? They're the eigen. This is a geometric way of suggesting that these are eigenvectors. Of the shape operator, right? Because those are the eigenvalues are the principal curvatures. And it's almost immediately obvious if you look at the matrix up here, right? If f and m are both 0, right? So f being 0 makes this happen because that was this problem. M being 0 sets these off diagonals going, and it's just diagonal. And if the matrix is diagonal, then the eigenvalues are on the diagonal, and they're just L over E and N over G, and that makes the basis an eigenbasis as well. But of course, you can also just, you know, follow the formulas. S of xu is literally L over E xu. That means that xu is an eigenvector with eigenvalue L over E. It also, going back to the definition of principal curvature, means that xu is a principal vector and has, you know, the principal curvature L over E. and likewise for xv as principal curvature n over g. So, if you've forgotten, go back and look up the definition of principal curvature again, right? So, now, so the eigenvalues, the principal curvatures, K1 and K2, are this over that, and that over that. Again, I'm not sure which one is first and which one is last, depending on, which one's smaller, which one's bigger. It depends on what L and N are, right? But in this very special case, the Gaussian curvature is just ln over Eg, and the mean curvature is L over E plus n over G divided by 2, which, as I mentioned a minute or two ago, would be what you get from the determinant, or the trace of that matrix. Although, I guess here we're assuming further that m is 0, so that if m was not 0, it would be a little bit cluttered, a little bit more clumsy, but that wouldn't change. So that's kind of a fun problem. All right. That brings us to section 5.5. Now, section 5.5 is kind of a it's almost a digression. I don't know if this matters too much elsewhere, but it is a very interesting calculation, so I'll try to go through it somewhat quickly. And basically what he endeavors to do here in section 5.5 is to describe how to calculate the shape operator with respect to a level surface, right? So if you've defined your surface by g equals to 0, the gradient of g, of course, gives you the normal vector field, right? And then he's calling it z, and so to make it a unit normal, you have to divide by the magnitude of z, and then we choose to use the usual covariant derivative stuff. The covariant derivative in the v direction of u is, well, you've got a product of the reciprocal of the length of the normal to the normal itself, and so the product rule gives you this and that. So we have the shape operator is minus, remember, shape operator is minus the covariant derivative of u in the v direction, and so by the product rule it gives us the two pieces, all right? Yeah, there it is. Now, of course, this piece is in the normal direction because it's a function times the normal vector field, whereas this piece over here is in the tangential direction. Well, see, that's not... see, that's not quite true. Well, in any event, I know that overall this has to be in the tangent, right? We proved in a previous lecture that the covariant minus the covariant derivative of u as long as his v is tangent to u, the value of this thing is in the tangent space to the surface. So I suppose this is manifestly normal. This must also have a normal piece in it. Notice that, well, anyway, let me not say too much more that I haven't verified directly. There's something, I don't know, I'd like to work out some more calculations for this section, honestly. But I haven't done it yet. So anyway, still the case that we have these formulas for the shape operator and with respect to the Gaussian curvature and the mean curvature. And if we have v and w tangent vector fields to m, such that the cross product of those tangent vector fields is the normal field, well, then some kind of neat stuff happens with these formulas because, well, v cross w is z for one thing, so this gives us k times the length of z squared, and this over here, well, remember that this is s of v and this is s of w, and then you dot with z. Now, the z cross z piece is 0, of course, so we only really have to worry about the covariant derivative cross the covariant derivative, and we get a minus minus gives me plus, and we get length z squared. All of that gets dotted with z. And so then divide by the length of z squared, and you got this formula. All right, great.